I can Hassan Molly.
Hi
Thank you.
everyone, hi from Melbourne. First, I should mention our weather is quite windy here, so I hope nothing goes wrong with the internet connection at home. I don't have the IT people in RMIT to help me out and fix it, and I'm not very good technically. Anyway, nice to be able to chat to all of you today. My area of expertise, as Hassan mentioned, is statistical quality control. And over the last few years, I've been heavily involved in the application of it in the medical area. Uh, while statistical quality control is well recognized in manufacturing industry, in the area of medical, started to be applied. And so a lot of things that we do is new. Um, Today, I'm not going to go through the mathematical detail, but I like to talk about three cases that we have been applying in a medical area. The first one is the application of multivariate control chart in monitoring the condition of the patient who have come out of the open heart surgery and are placed in the ICU unit. As you can see from the picture, or if you have seen someone in the ICU unit, usually there are so many machines attached to the body, and each machine is measuring one quality characteristics that is important to monitor the progress of the patient. The problem is in medical area, these several quality characteristics that define the condition of the patient in different area are correlated. And what the machine is doing, in fact, is monitoring it individually. And through the talk, I want to show you how misleading that could be in terms of medication, and what a huge difference that is when you have got a experienced surgeon looking after you and a surgeon who doesn't have as much experience in the area. The reason for the work was actually a few years back. We had a medical practitioner who was working in the ICU unit emergency section, and he decided to do Master of Statistics with us and did the quality control with me. And after that, he contacted me and said, I think you should send some of the students to collect data, and we should start looking at the application of multivariate in monitoring the patient. The aim of our research was to reduce human error. What is the human error? You see, if you don't have a very expert or very experienced surgeon in hand, if the machine is saying that the heart rate is going above the normal or dropping below the normal or temperature, the experienced surgeon knows that there is a relationship between the heart rate, temperature, blood pressure, and so on. So it doesn't start giving quickly a medication to reduce the heart rate. So it look at the other characteristics and then make a judgment. But an inexperienced surgeon doesn't have that expertise yet. So through application of multivariate quality control, we are removing that human error. We have to use multivariate control chart, and three commonly used multivariate control chart are T-square chart, cumulative sum technique, and exponentially weighted moving average. These charts are capable of monitoring the mean or monitoring the variability. Well, of course, in a lot of clinical area, monitoring the variability is very important, because when the patient is in a critical condition, they're trying to monitor the movement of variability in different quality characteristics. But today talk, I would only concentrate on monitoring the mean. The difference between these three charts, T-squared chart is commonly used, is easier to set it up, is easier to interpret it. So still in a lot of industry, they're happy to use it. However, the decision that you make in using a T-squared chart is you pick up a sample at time I, you calculate the statistic that you want to plot in the chart, and this statistic is only a function of your current reading. Doesn't take into account what was happening previously in this process. Cumulative sum and exponentially weighted moving average, these two charts are charts with the memory. The reason is the statistic that they plot at time I, when you pick up your ith reading in the process, is calculated based on the information on the current sample and all the information on the previous sample. So when it comes to clinical area, and my PhD actually was applying to some technique in monitoring the breast cancer patient through the temperature. So when it comes to clinical area, I would always prefer to use cumulative sum and exponentially weighted moving average. And also another thing that in the clinical area we should consider is, unlike industry here, usually you have a sample size 1. So you pick up some reading from the patient and you have to make your judgment based on that reading. You don't look at the average of the reading over a couple of measurements and so on. So we are dealing with a sample of size 1. The data that we had in this project were 9 quality characteristics. Among these quality characteristics, the CVP is a very critical characteristic. And the reason is the CVP, if it is greater than 80 in reading, then the condition of the patient is very critical. So out of, I think, 23 patients that we had, 12 of them had CVP greater than 80. And I'm concentrating today talk on those groups. For each patient that had 9 quality characteristics, on each quality characteristics, we had 23 readings. The measurements on these quality characteristics is done every half an hour as soon as the patient is moved into the ICU unit. And 4 hours after that, they measure it every hour. So the period of sampling is different. Well, first we thought, okay, we do some basic analysis like test of normality, if the characteristics are not normal, we use Johnson transformation, inverse transformation, and log transformation to make it normal. And then we did the test of variance because we wanted to know among these patients whether the variability on different characteristics are the same or not. And then we use multivariate control chart, particularly EWMA. And because we only have 23 patients, then for each patient, we try to fit a multivariate normal distribution when we transferred all the quality characteristics to normal, and use that fitted distribution to simulate 200 data per patient. So in fact, later on in the simulation, we had for patient 1, 200 similar situation and so on. I just put a couple of examples for you. In the first plot, I'm looking at one of the quality characteristics that was important, and I'm comparing the reading for the 12 patients that we have, and you can see even though all of them are in CU, the reading are so different, and the next one is for the blood pressure and so on. So definitely different people had different data. Then we looked at the time series plot for different patients just to see how these measurements are moving together and give us some idea on correlation between them and relationship between them. Then we carried out normality test. Normality test really, if you want to use exponentially weighted moving average, is not necessary because you can exponentially weighted moving average, one of its significant properties is not sensitive to normality. But because we were going to have simulated data, we needed to transfer all the data to normal and create a multivariate normal distribution. So we carried out transformation for the data that were not normal using inverse ln and Johnson transformation. And then we did test of variance equality, and we knew that, but obviously the variance were different. And then we did the correlation metrics to see how correlated data are. And in the clinical area, if the correlation is very, very strong, usually we get advice from medical practitioners, and we include one of them in the model. There's no point to put both of them. So after we did the basic statistic, we tried to develop our multivariate EWMA chart. I told you earlier, these are charts with the memory, and the statistic that you are plotting at any given time in the multivariate EWMA chart is defined by this statistic. So here my sample size is 1, so I haven't used the mean. So you have got the reading at time I, but what you are plotting is ZI, which is the weight constant lambda multiplied by your current reading. And you can see that I have the factor of 1 minus lambda applied to the previous reading. And if I open it up a little bit, that is how it looks like. Your weight constant lambda is between 0 and 1. There are 3 beautiful properties in this chart. The first one is, as you can see, the value that I'm plotting at time I to judge whether the process is in control or not is a function of all the previous reading. However, I can play with my weight parameter. If I select a weight parameter of, say, 0.2, that means I'm only contributing 22% to the current reading and 80% to the previous reading. And when you do that, then your chart is capable of picking up the small shifts. And throughout this project, we try to use a small, to monitor a small shift in the ICU unit, so we use lambda 0.2. The second beauty of this chart is that the weight, what you have calculated at time I is a forecast of your reading in the next step. So one step forward only. So in the clinical area, it is good because I can measure the heart rate now and I have some idea of what would be the reading in the next period that I'm going to measure heart rate. You can calculate the error of your forecast by subtracting this ZI from XI plus 1. And you can also use optimization and optimize the value of your lambda to reduce this error of forecasting as much as you can. So multivariate application is in clinical area is good. In the finance is also good. Those of you who are familiar with the time series, one of the model in fact is EWMA, but you can only use it for one step ahead, not more than one leg ahead. And if you are in the market as a quick buy and sell, then sometimes using multivariate, sometimes using EWMA is good because it gives you some idea based on the previous behavior of the share, what would you expect the next time. So, and also, as I mentioned earlier, this chart is not sensitive to the normality, and a lot of clinical data do not follow a normal distribution, and you have to do some transformation. So for this reason, I use the EWMA, multivariate EWMA for that. Okay, so what we did was we first of all constructed the multivariate chart for each patient separately because we are monitoring each patient separately. And then I put all the 12 patients together. But when I did that, you have to use a mean vector in your chart. The first mean vector that we used was what was recommended by medical practitioners for the heart rate and each of these quality characteristics. Then I put all the data together and we calculated the grand mean and we set up one chart based on that. And then we use the actual data that we have collected it and we use the mean vector and standard deviation of the actual data. So the charts that, the first chart in fact is the multivariate control chart for the first patient, and here we have used the mean vector recommended by medical practitioner, and of course we were expecting that that wouldn't, a lot of data would be outside the control because these are patients in critical condition and do not meet that level of mean for different characteristics. The next one is when we use the grand mean, it still is not performing well, but we can see that the number of out of control or being away from your upper control limit is not that bad. And then we looked at the multivariate chart for patient 1, considering all of its quality characteristics. Using the first one is based on mean and standard deviation of the actual data, and you can see that the condition of this patient is only in control at the time that they were taken sample of 70, whatever time it was. Now, when you use multivariate control chart in general, one of our biggest challenges is when the multivariate chart gives you out of control signal, you have to identify the individual characteristic responsible for it. In most practical cases, what they do is when they do receive an out of control signal, let's say for patient at time 1, then they look at the individual chart for each of the 9 quality characteristics and see which one is responsible or how many of those quality characteristics are really out of control at a given time. So if I look at the time 1 that we have got out of control, it shows that CVP at time 1 was out of control, the MPAP characteristic was out of control, and so was that PCW. But the reason that I said I want to show industry how confusing and misleading it is if they use only individual chart is here. You see, according to this chart, the condition of the patient is not good in general. But if they were going to use individual chart for each quality characteristics, you can see in this chart only in terms of this quality characteristic. In the first 4 reading, it was out of control, and the rest is falling inside the control. And so is this one and that one. So that was just to show them that they have to use the multivariate control chart rather than individual chart. And the reason is individual chart do not take into account the correlation between different variables. And in this graph, what we have done is we just highlighted the points that we have got, and then we are comparing it in the individual graph to see what is happening. Of course, this one was out of control, and so is out of control in the rest of this graph. But this one is also out of control, and if I look at these three independent variables, all those three are in control. Then we put all the 12 patients together, and here I have put a plot of T-square chart for you to see. The T-square chart is, as I said, is easy to set up, but it usually monitors the large shift and give you signal if there is a large shift occurring. So the first chart is the T-square chart for the 12 patients who were in the critical condition. And we have used the mean and the standard deviation of observed data. And this chart is the multivariate EWMA chart for the same patient, again, using the mean by the practitioner and using the mean of all of our data. And you can see that the number of out of control are completely different with the number of out of control that T-square chart is giving to us. The reason is the chart, EWMA chart, is designed to pick up the small shift as well, and that is why you have got a lot of out of control signal. Then we did simulation. Each patient had 23 reading, and we simulated data for 200 patients for each of our individual patient. And again, I'm looking at a T-square chart for 200 patients that more or less had similar condition as patient one, and you can see your T-square chart present all the 200 patients, or the condition is in control. And then we are looking at the multivariate chart for the 200 patients, and you can see here some of our patients are out of control. And as I said, then the practical or the common practice is then they look at the individual chart and they see which of these charts, and EWMA is your individual chart for, say, heart rate. And you can see that for some of these patients, the out of control signal that you are giving for this reading is similar to the one that individual chart give you, and sometimes it's not. That is the problem with using univariate chart. Now, the common practice to find the cause of an out of control signal is most often just looking at individual chart. However, in the past couple of years, we have been working with the people from machine learning area, and we are applying machine learning in detecting the most significant variables that are causing your out of control signal. But of course, machine learning, it makes it a bit hard for everybody to apply. But what we do with the machine learning, then we fit all the correlated quality characteristic into the system, and the machine not only pick up the most significant one, we have programmed it to give us, to even rank them for us. So it will tell us that, look, the most significant reason for the out of control signal is heart rate, and the contribution of it was 40%, followed by blood pressure with a contribution of 39%, and so on. And machine learning is good because then it allows us to use our resources in the area that is most needed, and then go through it forward. We have published a couple of papers in using machine learning in fault diagnostic. So the conclusion of that was multivariate control chart is good. You can still to some extent use univariate chart to investigate the cause. If you are transferring your data, then you can use the T-squared chart, as long as you remember it only detects the large shift. Otherwise, EWMA is good. We also showed that the three means that we have used, the grand mean and medical practitioner recommended mean, are not working very well, and the estimated mean based on data is working better. And so the rest of it, as I said, memory plotted chart are the one that we usually recommend, especially in the clinical area when you want to monitor the small shift. And the good thing about EWMA is not sensitive to the normality. The next topic that I want to talk about is using a statistical quality control in reducing maternal mortality rate in South Sudan. Now, I had a Sudanese student who did, again, our master program and did the minor thesis with me. And then he said that in South Sudan, apparently, the maternal mortality rate is very high. And is there anything that we can do using a statistical quality control to help it, or at least help in resource allocation? The statistic is shocking because in South Sudan, unfortunately, 1 out of 7 expected mom die. Which is very, very high. Comparing with the other countries, in Africa, 1 in 15 die, in Asia, 1 in 105, and in North America, 1 in 3,750. So we said, okay, let's see what is happening. That is a practical sort of situation in South Sudan for expecting mom. They have to walk sometimes 5 miles in really rough roads to get to a clinic. And when they get to the clinic, of course, the facility are very, very limited. And usually there is a midwife or nurse who can just give them some advice and so on. So what we decided to do was, first, let's look at the influential causes of maternal mortality in the country, and then let's find the best model to describe mortality in terms of these significant factors. And then when we did all of that, we developed profile monitoring that I explain in a second what it is. Now, when you're working on the clinical data, usually you have problem with the data. And when you want to work on the developing countries, then you have got a bigger problem because data don't exist. Often, if they exist, some of them are not reliable. And even if you can get access to the reliable data, like in the university hospital and so on, then the problem is these data are recorded manually, and you have the task of transferring it into electronic sort of database to be able to do some statistical analysis. And for this project, actually, first of all, South Sudan is a developing country, and there are a lot of charity organizations such as Voters Organization and Madeline Foundation and so on, who are present in South Sudan, and they are trying to help, and they are aware. And when the project started, we had a connection with all of them in South Sudan. They were very much in favor of the project, and so a student had to go there practically for 6 months and collect data from the only reliable section that we knew, and that was the university hospital in the capital. So that is how we collected 15 years of data on mortality rate. Now, when we looked at the causes, first of all, in the mortality, maternal mortality rate, we had mortality rate when the mother also had HIV, and that is common. And then we had mortality rate when the patient didn't have HIV. Because HIV had other significant things coming with it, so we try to separate, and the information is now based on non-HIV mortality rate. The HIV mortality, both mortality rate, the charity organization are working, the government is online with them, and it is coming down, but unfortunately, mortality rate for HIV mothers is coming down much slower than the mortality rate for non-HIV. So our work was on the HIV. We also, when we look at it, the mortality, there were so many reasons, and we had to separate them. There were economical reasons for it. And so we looked at all the economical reasons, and the three that stand up in our modeling was the patient not attending the skilled personnel at birth. It was the rate of fertility, which is very high, and it was the GDP, of course, the, what is the condition of the mother and so on. There are also factors such as road transport and so on, and we looked at it in a different situation. We also had the causes which are physiological causes. So we looked at the mortality rate just due to economical causes and mortality rate due to physiological causes. With the physiological causes, similar to every other developing countries, these were the most common causes. On top is always hemorrhage, unfortunately, and that is heavy bleeding, either prior to delivery or after delivery for 24 hours or 48 hours, and then the mother died. And there are other things. Now, again, in this list, we consulted the authority, and they said hemorrhage is something that is very high, and we could do something about it through training and so on. Also, unsafe abortion is quite common. Rape apparently is high because the country is in war. And also the age of marriage starts from 9 in the rural area. So some of them have got the first baby or expectancy at age 12. And so there is a lot of unsafe abortion. And in the rural area, there are sort of group, and the head of that group would tell them what to do rather than they come and see a skilled person. Infection and other problem while there existed, but there were other things that we had to control. So we try to concentrate on the hemorrhage and unsafe abortion through our team. So first, we look at the economical data. As I said, skilled attendance at birth was a huge reason for the mortality rate, and also the rate of fertility, which is quite high. And of course, it was GDP. When we looked at the data for GDP over 15 years, because the country is in war, the changes from year to year wasn't that significant in the model. So we tried to treat it as a constant, and we just took the average GDP over the 15 years of data collection. And so we developed our two models. We tried quite a few models that were suggested, and log linear regression and Poisson regression came up to be the best one. So before we do it, we used our data, and because in the mortality data there was a downward trend, so what we decided to do to build a model and keep some testing data, we use binomial distribution to select the data, 2/3 of data for model building and 1/3 for testing. And so we looked at the testing based on the real data that we had and mean error and standard deviation of the mean, and it looked like that log linear regression was performing better, even though the R square was slightly lower, and you can see the plot of the data. So now that we have got a regression model like that, or a mathematical model like that, the next phase of quality control is profile monitoring. Earlier, what we said was we are only monitoring one statistic based on our reading. In a lot of situations, what happened, first of all, these are some information on the previous model. So if we increase the skill attendance rate at birth by 1.22%, the mortality rate could reduce by 1.4. And if we if we increase the skill attendance at birth, then we would have mortality rate reduced by 1.4. And if we reduce the fertility rate by almost 1%, then the reduction in the mortality rate would be 16%. Then we moved into now monitoring this relationship between mortality rate and these economical factors. Here is when profile monitoring comes into the equation. In the profile monitoring, you have a phenomenon that depends on some other independent cases and key performance indicators. And your aim is to monitor the performance of this phenomenon when these independent key performance indicators are changing, and monitor it to some extent. And that could have been applied to the mortality rate very well for the following reason. World Health Organization know that the situation is really bad, so they have set up a plan through the charity organization that they have to do everything that they can in the country to reduce the mortality rate between 140 to 70 by 2030. So we had these two limits to start with to develop our profile monitoring. And because the profile monitoring, the equation that we considered and was performing well, had two independent parameters, skill attendance at birth and GFR. We used the optimization procedure to see if we want to get in 15 years to the value recommended by UN, which was 140 and 70, how we can simultaneously optimize the value of SAB and GFR. This paper is published in BMC, the result of this work. And so optimization procedure give us this. So we started with the value, the reading of mortality, number of deaths in 2015, which was 730. We are reducing these to 140 and 70 by 2030. And then skill attendance is something that we want to increase. So we looked at the maximum in the last 15 years, and we said that would be the starting point for your constraint. And then the GFR, because we want to reduce it, so we started with the minimum value existing in our data, which was 175. And so in the first three columns, we are targeting the mortality rate of 140, and in the next treat the mortality rate of 70. And this is giving the government a good idea where they should put their resources. So by 2030, if they want to achieve 140 mortality rate, they should increase the skill attendance rate by average of 50 from 19, and they have to have enough training to be able to have that. And also they can use different training, education, and you know, PEEL and so on, to reduce the fertility rate from 175 to 97. And when they are moving that to the target of 70, then they have to increase the skill attendance from 19 to 76 and increase their fertility rate from 173 to 76. So that broke it year by year for them to see how they can allocate resources to train more personnel or to educate people in terms of, you know, not having more children and so on. And this is the graph that we came up. So that is in fact the boundary for the regression equation that we have designed, and that is the boundary per year for the SAP and for the, for the SAP that is increasing, and for the GFR which is decreasing. And this is the individual one. So the hope was now they have got a number year by year that they can target. And here, while they have got the upper and lower value for the mortality rate, at least there is a middle value in there that they can target. Then we move to the physiological causes, and again, the data that we collected, we did some histogram thing, and we could see from the collected data that 30% of the deaths are due to hemorrhage and about 8% to unsafe abortion, and these were the two that we considered to work with. And we separated now. So the mortality rate that we are considering is only those caused by the physiological causes, and the target that we are considering from World Health or from UN is the number of causes due to physiological causes. So we first looked at the full model, and again tried different models, and Poisson was performing good, and putting all of your variables in, we had the R score of 97.3, which was very good. So we tried now to look at a reduced model, just, you know, make it smaller so people can do something with it. So we just use the hemorrhage and unsafe abortion, and the model is still based on these two characteristics. Is explaining 92.8% of 7% of the mortality rate. So it was good enough for us, and you can see the error estimation is quite good. And so now we targeted the UN 2030 this based on physiological causes. That was 43 and 21, and we went through the same procedure. We are trying to minimize both of these numbers, the number of hemorrhage and the number for unsafe expectancy, and give them some idea of profile monitoring, how they can year by year monitor this number, and or at least do resource allocation to make sure that these numbers are controlled. The next topic that I want to talk about, Hassan, if I'm going over the time, please let me know. So the next topic that I want to look at it is using profile monitoring to reduce the newborn mortality rate. Again, this is a topic that raised with, by one of my master students from Indonesia. Her mom was a midwife and she did the master with us, did the master minor thesis on quality control. And she said that, this is a huge problem and we have to address it. In fact, the newborn mortality rate recommended by UN and World Health Organization is 5, and in Indonesia, in some of the states, is 37. And in fact, she was living in one of the states with highest newborn mortality rate. Okay, so what do we do? When a mother is expecting, between week 4 to 40, when they know the result that they are expecting, and 40 is usually the week that they give birth, it is important that we monitor the growth of infant inside week by week. And if we can do that, then we can have intervention on time to prevent unhealthy expectancy. And you see, expectancy to me was a process. It's a process that takes 9 months. There are parameters that you can monitor within these 9 months, and the final product is a healthy mom and a healthy baby. So it was a sort of process, but not industrial process. When we looked at the causes that, there is the newborn dies, one of the most significant causes is the delivery weight. In fact, if the delivery weight is less than 2.5 kilos, usually either they don't survive, or if they survive, there are consequences in their life, including learning difficulty, heart problem, and so on. And if their weight is greater than 3.9, again, there are consequences later on in their life, like high blood pressure, diabetes, and so on. So we had to find a way to predict the delivery weight while the mother is expecting. And if we can see at different stage that the baby is going to be underweight or overweight, then intervention can happen, and hopefully we can prevent the bad consequences. This project was very challenging because the aim was to come up with a model that is simple, doesn't need any sophisticated instruments such as ultrasound. And it can be implemented by a midwife who is working in the rural area. And 86% of expecting mom in Indonesia apparently are seen and monitored by the midwives. Those are the frontline medical practitioners in expectancy. And so we had to come up with a simple model that is reliable, and yet it can give some estimate of delivery weight. So and also the problem in the clinical area is one model doesn't fit every nation. So the model that could be built based on the local data usually is more effective than international models, even though in some of the international models, what we do is we create some sort of connection and some sort of constant and factors into the model to be adopted to different nations. I will show you in a minute that it doesn't work. So we did a lot of searching, and the student went back to the country, did training, and the government was really working with us because that is a big problem and they want to address it. So they released about 19 midwives who are working in the rural area, servicing 26,000 expecting mom to attend this workshop and training. And so the student could collect 6,500 data through this training program, and we could build a model. And the model that we built came up with this. Now, that is the estimated fetal weight at different stage of expectancy based on only fundal height, which is something very simply measured by a meter, by even ruler in the rural area. But this doesn't give us the relationship between the weight and gestation age that we wanted. There is a relationship, so students start working on it, and when we have got the fundal height, we can estimate GA, and so that would be the model that we will use to estimate the fetal weight at different stage of expectancy.
Sorry, Maury, interrupting you. 3 minutes left.
Okay, so I go directly through the thing. So this is the function that we used actually to set up our profile monitoring, and we looked at the different data and the error of estimation. And this paper is submitted for publication. I couldn't put too much of the details in it in the paper, but that is the profile limit that we came up, upper and lower, and as long as they can estimate the weight at different gestation age and is falling in between, they are okay. Otherwise, they should use intervention to see what's happening. There are models developed at international level, and this is one of them, the most common one, and we applied that to the Indonesian data normal births. As you can see, that is not fitting. So putting it together with our model, you can see the model is performing very well. And that is based on the normal weight. Then in the data that the student collected, after that, 460 of them, there were 16 low birth weight data, and you can see that applying this model, 68% of the low births could be picked up between 20, week 20 and 40. So we could say that the model can prevent and give us warning. Thank you. I'm finished.
Thank you very much. Thank you very much for on time finishing your talk. That was amazing. Thank you. Any question? You can unmute yourself. I think I can unmute. I unmute everyone. If you have any question, maybe I can ask my question. I have seen different growth chart in your report. I'm just wondering, do you use quantile regression in just?
Yeah, actually the one that we developed, in fact, and as I said, because that is submitted, I had to remove some of the calculation because it's under review. But yet, we use the regression, and we use some of the percentile point on developing that chart based on our own data. That was the significant part of this development, that using our own data, and we were so lucky to have 6,500 to start with, and after the training we could collect 450 data to test the model that we have developed. But yes, that is what we use.
Yeah, that's good. Any other question from our audience? Can I ask another question?
Sure.
So I'm just wondering, in all of these projects, you have used parametric statistic, for example, linear model or generalized linear model, log linear. I have seen log linear in your talk as well. Do you try non-parametric method as well in your projects?
They have just started, but you see, there isn't much work on the non-parametric situation when you move into the profile monitoring development and so on. In the profile monitoring, really, majority of them have worked on the linear models. But yes, a student, in fact, the Indonesian a student who is now finished and is back in her country teaching. She's continuing with the non-parametric.
Oh, yeah. Thank you very much.
Thank you.
I think we don't have question. So thank you very much, everyone, for joining us, and have a lovely weekend. Thank you.
Thank you.
Thank you for your time.
Thank you. Bye.
You can stop
You have
here.
a good
Thank you.
weekend too.
Bye-bye.